By far, the most common operation within symmetric cryptography is symmetric encryption. Let's talk about it. Symmetric encryption takes plain content, readable to anyone, and turns it into something unintelligible. Then, it subsequently reverts it back to its original form. Doing this second part is critical, because it doesn't make sense to encrypt something if you or someone you trust can't later undo it at some point in the future. Here's what this looks like visually. The plaintext is the content before it was encrypted and readable by anyone. You take that plaintext and combine it with an algorithm and a secret key that's going to produce ciphertext. The ciphertext is the unintelligible form of the original plaintext. Then you can take this ciphertext and decrypt it using the same secret key as you used to encrypt it to revert it back to its original form. A good way to conceptualize this is to consider symmetric encryption as a simple mathematical operation. For example, let's say our plaintext is the number 6. In computing, any data is just a bunch of ones and zeros, so it's easy to translate that into a number. You can take this number and combine it with a particular encryption algorithm. For our example, let's use multiplication. And for a secret key, let's just use another number. For this example, we'll use the number 7. Well, 6 times 7 equals 42. 42 is the ciphertext, which is the encrypted version of this plaintext. Then, for decryption, I'm going to use the inverse operation. If we used multiplication for encryption, I'm going to use division for decryption. And again, I'll use the exact same secret key I used during the encryption process, which means 7, and 42 divided by 7 will equal 6. 6 is the original number that I started with. Okay, so why would you use symmetric encryption? Well, the purpose of symmetric encryption is to ensure that only the intended party has access to the original data. For example, if I gave you the number 42, there's no way for you to know that the original message I meant to send was 6, unless I also gave you a copy of my symmetric key of 7. This provides a cryptographic concept known as confidentiality, which states that only the intended party has access to the original data. And that intended party is sometimes someone else that you're trying to speak to securely, and other times it's yourself in the future. For instance, if you write an encrypted file to a hard drive and want to access it later. Now, the actual math behind symmetric encryption is highly efficient. That's what makes symmetric encryption suitable for protecting bulk data. Meaning you can use symmetric encryption to encrypt all the packets that you're sending out to the internet. Or you can use symmetric encryption to encrypt all the files on your hard drive regardless of their size. Here are some algorithms which can be used to perform symmetric encryption. These 3 are considered legacy and are no longer considered secure enough by today's standards. These 4 are all considered secure enough by today's standards, and the most common of these you'll see is AES 128 and AES 256. AES, or the Advanced Encryption Standard, is one algorithm that can use 3 different key sizes. ChaCha20 is another algorithm, and it uses a 256-bit key. The future for symmetric encryption involves finding algorithms that are quantum safe. The idea there is that there are these quantum computers that are being developed that'll be effective at breaking many cryptographic algorithms, but not all of them. The ones that are safe from being defeated by quantum computers are known as quantum safe. And lucky for us, AES and ChaCha20 are both considered quantum safe algorithms, so we can expect to continue using these algorithms for the foreseeable future. That's it for our lesson on symmetric encryption. In the next lesson, we'll be looking at message authentication codes, or MACs. I hope you enjoyed this video, thank you for watching, and I'll see you in the next one.